introduce the last day of this conference and the talk by Dhruv Ranganathan from this university. He will speak about Gromov-Witten theory and the topological.
Okay, thank you. Thanks everyone for staying until the Friday. It's always, yeah, so thank you for the invitation. It's great to be able to visit the Isaac Newton Institute. Everything I'll say today is joint work with Davesh Maulik. So it's a talk entirely in the world of Gromov-Witten theory. It's related to some questions in Donaldson-Thomas theory, although that will make no appearance today. We've been thinking about some questions about Gromov-Witten theory and DT theory and the technology that we developed helped us answer another question that we were interested in, and that's what I'll try to share with you. So the story of the talk in some sense is about the interaction between Gromov-Witten theory and the moduli space of curves. And so just to get us started, I'll fix a smooth and projective variety, smooth projective manifold. And the sort of central player in Gromov-Witten theory is this moduli space of stable maps to X. Okay, so we all know this, but just to get us all on the same footing, so we're interested in this world to study stable maps from some curve of a fixed genus to some variety, okay, X. We have n marked points on the curve, okay, P1, P2, Pn. So beta is going to be the topological data, so the curve class of the image, and I fix the genus. And the basic, so there are lots of experts in Gromov-Witten theory here, but there's only three things that I really want to highlight about this moduli space. So three things about this space of stable maps, and they'll all come up. So the first is that, well, it exists. So MGN bar X beta, so this is proper DM. I guess that's what exists means. Second is, so it's not smooth, but it has a sort of smoothness property. So it carries a certain class, which has also come up earlier in the week. So MGN bar X beta has this virtual fundamental class in homology. Okay, so I'll write just expected here in some expected dimension that I just don't want to write down the number. And okay, so it's first thing in the morning, so we should say something about the virtual class. So give or take, certainly in good situations, MGN bar X beta, just by virtue of being a moduli space of something, comes with a preferred description as, let's say, an intersection of two smooth spaces inside of a third smooth space. So that's just some preferred structure that it has. And because of that preferred description, the sort of intersection product of those two smooth spaces inside that third smooth space gives us a distinguished class, which, if everything was beautiful, would just be the fundamental class of that manifold. But we can always make sense of this virtual class. So in general, that's not quite true, but it's true locally and incoherently enough that this structure still makes sense. And there's only one feature there's an important feature about this that I want to mention, which is that this is the class, the virtual class, is insensitive. Okay, it is a deformation, so deformation invariant. And what that means is that when I change the complex structure on X, if I take a deformation of X to another smooth projective manifold, then the virtual class in an appropriate sense will stay constant. So just a good one to keep in mind is, if X is, for example, a K3 surface and I deform it, then all the curves should go away and the moduli spaces will become empty. That tells you that the virtual class is 0, even though the moduli space itself is not constant. Right? So the moduli space changes, it jumps from, well, it jumps away, I guess. It goes from being non-empty to empty, and so the moduli spaces themselves are not constant, but this virtual class is constant, in that case just 0. Okay, so this will, I want to emphasize this point because it will come up soon. And the third property is that this space, it doesn't just live on its own, it has some tautological morphisms So mgn bar x beta evaluates to x to the n, because if I have a curve mapping to x and endpoints on the curve, I can just follow where the endpoints go, and that takes me to x to the n. But also, if I have a curve with a map to x, I can just remember the curve and go to the moduli space of curves. I'll call that pi. Okay. So that's just our setup. The sort of main character in the talk are what you might call Gromov-Witten cycles. Okay, so a Gromov-Witten cycle is any class of the following form. So I pull back cohomology class from this space of evaluations, some gamma, I cap it with this distinguished virtual fundamental class, and then I push forward. Okay, so we've seen versions of this construction several times throughout the week, so it's just a very natural thing to do. MGNX, just by virtue of this diagram over here, the virtual class is a distinguished kind of correspondence between the cohomology of x, or the cohomology of x to the n, and the cohomology of the moduli space of curves. And these classes are the sort of maximum capturing of that information. Right? So it just tells us how MGN bar interacts with some random variety x that you might be interested in. And so the goal of the sort of overarching question in the talk and in the sort of line of inquiry is to understand where do these classes live? Where do these Gromov-Witten cycles live? Okay, so I'm going to just pause for a second on a technicality. Okay, important technicality. So throughout this talk, I'll be working in homology or cohomology of the moduli space of curves. And by that, I in particular mean not Chow. Okay, so Chow is a totally different story, and for once, it actually matters. Okay, so we're guided in answering this sort of vague question by a speculation / conjecture. The speculation is, I think the first time it's stated is by Levine and Pandharipande. This is in their paper on algebraic cobordism, although the exact link is maybe not so clear. This is around 2005, the statement goes back a little bit further. You know, at the very least, there are papers of Faber and Pandharipande that don't state the conjecture, but they prove theorems that would make you ask the conjecture if you were, well, I guess if you were reading the paper. Okay. So, the speculation is the following. All Gromov-Witten cycles, they lie in the tautological subring of the cohomology of the moduli space of curves. Okay, I'll work with Q coefficients throughout. Okay, so that's the speculation. I'll discuss the speculation in some detail, but let me just say a word about what this means again. So the moduli space of curves is a beautiful space, but its cohomology is rather intractable. Okay, so we don't. It's one of these things we don't expect to ever understand, I think. But nevertheless, there are classes there that come, in some sense, just from the fact that MGN bar is not just a single space, but it's a space for every G and N, and these different spaces interact. Okay? So, for example, MGN bar can be embedded. The simplest thing you can do is embed MGN bar into MGN plus 1 bar. Right? So how? Well, this is a curve with n marked points, and roughly speaking, I can add an n plus first marked point in several different ways, actually. So let's call this psi I. I can add an n plus first marked point by just putting the last marked point on top of the ith marked point. Okay, so technically that's not really allowed, and so you do the next best thing. I and plus 1 are on some kind of bubble, and etc. Okay, so etc., where etc. means gluing, and forgets what maps. Okay, so this is just one example, but you can also go from mgn. You can go from mgn to mgn minus 1 by forgetting the mark point. You can use the fact that a good way to build a genus G curve is to take two curves of smaller genera and stick them together. So this is all the moves that you get from the fact that you're considering nodal curves rather than just smooth curves. Okay. And so the tautological ring is, okay, the way to load it in your head is it's all the classes that come from taking the fundamental classes and then doing all the basic algebraic topology operations. Okay. So the tautological subring, or really, perhaps one should say subrings. So this is the smallest Q algebra of cohomology. So it should be defined simultaneously for all G and N, or all G and N, and is closed under push forwards. Under these natural operations. So, already, I think, without knowing anything about, okay, so you have to take one thing for okay, I'll discuss this in a second. So even without knowing anything about the tautological ring, I find this to be a somewhat interesting statement, because it's saying that all of these classes, which in principle depend on all the x's that you could have chosen and all the betas you could have chosen and all these cohomology classes on the target that you could have chosen, this is an absurdly large set of symbols in the cohomology of the moduli space of curves, but in principle this is saying that, well, they all lie in some subspace basically with like additive generators, right? So, okay, yeah. So already that is kind of interesting. It doesn't see x. Right? Okay, so of course there is another subring that doesn't see x, which is the whole cohomology. So the strength of the statement relies on a few facts. So let's discuss this. So the point I want to make is that this is kind of a wild speculation. It really is. It doesn't seem like a reasonable thing to ask for at first. So I just want to share why not. So a few things. So first, the cohomology of the moduli space of curves, famously, I said it's a complicated object, so in what way? So it contains classes, it contains odd cohomology, also odd classes, unbalanced Hodge classes, for example.
Why don't you just be non-PP?
Yeah, sorry, unbalanced in the Hodgson composition. So it contains, it contains these kinds of classes, but of course our construction is saying, it's the smallest set of Q algebras that is closed under push forward, so all of that is going to be algebraic, right? So forget PP, there's nothing complicated here. All of this is going to be algebraic. And so what does that mean for the speculation? Well, if you rig, right, so if you pick your gamma, you take your x that has lots of odd cohomology, you pick one of your odd cohomology classes, you pull it back to the moduli space and you push down, this is saying that guy had better vanish, okay? So already I think, even if you don't care about the tautological ring, this is probably like the most powerful computational tool in Gromov-Witten theory. It's very good at computing zero, right? Which is, okay. It sounds better if you say vanishing theorem, but yeah, very good at computing theorem. Okay, so but there's more. So cohomology of the moduli space of curves also contains algebraic non-tautological classes. And they're not mysterious. I'll tell you I'll tell you an example in a second. But this is saying, well, Gromov-Witten theory doesn't hit those either. So despite all of this flexibility, all the x's, all the betas, all of the different cohomology classes you you could try and take, you cannot describe, by this push-forward technique, you cannot describe a non-tautological algebraic class. Also weird, right? Why would that be? And it gets even weirder if I tell you where this comes from. Okay, so there is a non-tautological algebraic cycle. And okay, so in MG bar, for a large enough genus, the locus of what are called bi-elliptic curves. So, maybe. So, i.e. the locus of curves, so this is basically the set of curves C, with some marked points maybe, such that there exists a 2-to-1 map to P1. This is a locus, okay, this is maybe on smooth curves. This is the locus of curves that emit a 2-to-1 map to, sorry, not to P1, that's hyperelliptic E, or some elliptic E. So it's an existential, there's an existential quantifier that's important here. So there exists an elliptic curve such that your curve double covers that elliptic curve. That's the non-tautological class. It's not exactly mysterious, right? I mean, okay, it's basically something that comes from Hurwitz's theory, so you know, it's a 19th century class, and it's non-tautological. And I'm telling you that you can't hit it with Gromov-Witten theory, which you should feel a little weird, right? Because, okay, if you've played a little bit with the space of stable maps, here's one great variety that you can take as x. You can take M1 2 bar as x, or any elliptic fibration, right? And if I study maps to the fibers of an elliptic fibration in degree 2, twice the fiber class, that looks a lot like it's describing this, and yet they knew this and I know this. It's all fine. Okay, this does not falsify the speculation. So, yeah, okay, okay. So let me say something about known cases. I get to highlight the work of some people here as well. So when I say known cases, I mean cases where the conjecture actually holds, speculation actually holds. So the simplest case is when X is a toric or G mod P, and this is in some sense the first non-trivial consequence of the now famous virtual localization theorem of Levine and Pandharipande around the year 2000. Okay. So, oh, sorry. Won't compile. Okay, so how do you prove this? Well, you apply the localization theorem, and the localization theorem basically reduces arbitrary Gromov-Witten cycles to some kind of Hodge integrals on the moduli space of curves. The cohomology classes from the target itself, they sort of turn into bundles, right? That's sort of the nature of the localization theorem. They turn into Chern classes of bundles on the space of curves, and so you don't really see their complexity from the point of view of the target, okay? So should you be impressed by this? I don't know. It's very important. And of course, the theorem has been great for other things, but if you were trying to decide if you should believe this conjecture, maybe not, right? Because like there's no odd cohomology, there's none of, yeah. The target is quite simple. However, I think the following one should be a little bit more impressed with, which is that it's known if X is a curve of any genus. Okay, so this, there's some names here, probably, I think, so Felix Janda finally sort of killed this problem off, but a lot of ideas also go back to Okunkov and Pandharipande's determination of the Gromov-Witten theory of target curves. Okay, so a higher genus curve, this is known, and of course there is lots of odd cohomology. Well, okay, there's some odd cohomology in a higher genus curve, and the conjecture is known there. And then you can do some other tricks. So like if you have a toric bundle over a higher genus curve, you can get that. If you take a product of two curves, you can get that. But then there's actually very nice recent work. Okay, I can't actually remember when this was. So Argus, Bousseau, Pandharipande, whatever, Pandharipande, and Zonkin. This was a couple of years ago. So they proved that it's true for all complete intersections in Pn. Okay? So the Pn is important here, but nevertheless, this is a very large class of varieties. Okay, this is a pretty large class of varieties. Okay, So for all complete intersections in projective space, this is known. And then, because it'll be relevant later on, I just want to say one more thing. Yeah, I'll try and say more about this later on. I'll say one more thing. So it's also, this speculation has a sort of birational nature to it in the following sense. So if true for x and some z in x, then it's true for the blow-up of x in z. Okay, so this is Hu, Li, Ruan, and also Honglu Fan. So so that's an interesting one because it produces lots of examples. If you know the conjecture, so you know the conjecture for curves, for example. So if you take a curve in P3 and you blow it up, now suddenly you know the conjecture there as well. Right? So it gives some kind of birational nature to the question, some kind of birational nature to the question. It doesn't say the question is birational in nature, but it's close. Yeah. Okay. So let me state the theorem that I want to discuss today.
Can I ask something?
Oh, yeah.
You stated this speculation for classes in a cohomology of x to the n. Is that actually equivalent to like stating it just for n cohomology classes that you kind of pull back and that's not extra complexity?
No. Yeah, I mean you can. Yeah, you could do that, or you could take Kuna's components, or but it's all equivalent. Yeah, it's all the same. Yeah, absolutely. Thanks for the question. Okay. Any other questions while I'm here? Yeah. So it's kind of interesting. So the reason I find this speculation very interesting because it's like a very low percentage chance phenomenon. It feels like it shouldn't really happen, and yet it keeps happening. It's like, it feels like it shouldn't happen. It's like England winning the Euros. A very low chance of it happening. But nevertheless, Levine and Pandharipande are like the typical English football fan, and they're like, okay, it's coming home to the tautological ring. Okay. So everyone can relax. I'm not going to prove this theorem today. I'm not going to prove the speculation, but we're going to say something. So this is the theorem with Davesh. This is partially based on a paper from late last year and work in progress. So I'll explain this. Some of this is known, some of this is new. So the theorem is the following. So let x to b be an SNC degeneration of, maybe fancy x. Degeneration of our variety x, which I'll identify with a smooth general fiber. And let x naught be I'll draw a picture. Let x naught be the SNC special fiber, or a SNC special fiber. Okay, really, probably, okay. Maybe I want B to be a smooth projective curve, and this is a proper flat family that is smooth away from finitely many points, and at those finitely many points, the thing looks like a bunch of smooth hypersurfaces meeting transversely. Okay, I'll draw a picture in a second. Okay. So then, the statement is the following. Okay, so let me just introduce a piece of notation. So x naught is reducible, so it's a union of a bunch of x naught i's, irreducible components. And anytime you break a variety into irreducible components that are meeting transversely, let's say that y capital I is the intersection of the x naught i's over I and I. Okay, so what this is saying is that my variety is broken into a bunch of pieces, and so I can take the irreducible components, and I can take the double intersections and the triple intersections, and so on and so forth. Again, I'll draw a picture. I keep saying that, but I will. I'll draw a picture. Okay. So then the statement is then the Gromov-Witten cycles of xb lie in the span of the Gromov-Witten cycles of the yi's, of the y capital i's. Okay.
The span
here in the sense that like push forwards and all that stuff.
Yeah.
Span, or what do we mean by span?
Yeah. Maybe we mean span under all the tautological operations. I push forward the moduli space of curves. I take something. Yeah.
So
That's
this
right.
statement is not necessarily true in Chow.
It's false in Chow. It's false in Chow. So, and it's not false for a deep reason. So.
This was the curve.
It's false for curve. It's false for Chow 0. So Chow 0. So M111 bar, for example, that's the first place where probably you'll find a counterexample. So M111 bar has a holomorphic form, holomorphic 11 form, 11-0 form. And because of that, by work of Mumford, its Chow 0 is huge, but the tautological ring can only see a single one-dimensional vector space in that massive thing. And you can hit that. Yeah, you can hit any point if you set up the problem in the right way. Okay, so I want to talk about the proof of this theorem, which basically involves logarithmic Gromov-Witten theory and a lot of the technological developments that have sort of gone on in that subject for the last probably 15 years now. I have about half an hour to do it, so that should be fine. Maybe I'll say a word. So at first sight, so what does this say about the speculation? So.
What about your picture?
Oh yeah, thanks. Right. So here's X. Well, I would have gotten there. Okay. No, thank you. Okay, so B is a smooth projective curve, and X is some kind of smooth total space, and I have my my interesting Roman X in the fiber over some point B, and then I have some kind of reducible. Maybe I make this a surface so that this picture is interesting. Okay, and I have some kind of picture like this in the spatial fiber. So this is 0. The fiber has 3 irreducible components. Fiber has 3 irreducible components: x01, x02, and x03. And then it has these double intersections, which are the this would be something like, in my notation, y subscript the subset 1, 3, y subscript the subset 1, 2, and y subscript the subset 2, 3. Okay, and of course there's the point as well. Okay, so that's the picture to have in mind. And okay, I'm actually going to talk about the proof as well. But this, maybe just keep in mind these two examples of what x0 might look like. It could be like a bunch of different pieces meeting, or it could just be 2 pieces meeting. And the difference here, I'll explain as I go on, is sort of significant. Okay, so a lot of the juice in this theorem lies in the fact that we can handle degenerations with more than 2 components. Okay. Although even without that, I think some of these results are still new. Okay, so what does this say about the speculation? Well, it says that if you can degenerate your variety to a union of things where you know the conjecture, then you know the conjecture. So what should you imagine? Well, we have some examples on the board. So like complete intersections in toric varieties or in abelian varieties. These are both good because you can degenerate them in nice ways to unions of toric varieties meeting transversely. Yeah. Yeah.
So you need a complete family with a smooth.
For one little piece in the argument, it's fine. Yeah. Even without that, it's true. But yeah. So there's some Hodge theory in the background. It's this global invariant cycle theorem. So I want the target to be projected. But yeah, that's okay. I can have multiple singular fibers, and so.
But to compare, you only need 1.
Yeah, just 1. Yeah, that's 1. Okay. So yeah, thank you. Okay, so the speculation is now, so this theorem verifies the speculation for all complete intersections in toric varieties, or all complete intersections in abelian varieties, but because of the deformation invariance property of Gromov-Witten theory, it really does it for anything that's deformation equivalent to something that degenerates, right? So this is more useful than you might think, right? So if you try to fit a curve of genus G, some large genus G into this scheme, well, or into this scheme in the whatever, in the English sense. How would you do it? Well, you have to express your curve as like a hypersurface or a complete intersection somewhere. And for your curve, that's probably not possible. but okay, I can probably express it as a, like if I deform the curve, I can make it hyperelliptic, and now it's a hypersurface on P1 cross P1, right? So that's just to say it is useful. This deformation equivalence move is actually useful. Okay, so it treats it in that case, but it's sort of intrinsic. So it also treats it, for example, I think I have to verify this, but certainly this is all or most Fano threefolds, because Fano threefolds by results in the minimal model program, we know they admit good degenerations to unions of toric varieties, or things that are close. Okay, three is important, but also, if there's so basically what this theorem says is that every time you prove the theorem by hand for some class of varieties, this theorem upgrades that to some rather large class of examples. So. For example, one thing we know is that semi-simple, this I didn't mention earlier, but things with semi-simple, let me just write this. So varieties with semi-simple quantum cohomology, they also have tautological Gromov-Witten theory by reconstruction results of given cell Telemann. Okay, so there are other classes of varieties beyond just the toric ones, and this is really saying something about that. Okay. I don't know if even all surfaces are covered by this. And in fact, I suspect the answer is no. But, so where does this leave us with regards to the speculation? This is the last thing I'll say really about the speculation. Where does it leave us? I think it's hard to say. You really should believe it, but it's still up to you. So, I want to discuss the proof of this theorem. And I need my cartoon. So during the discussion, I want two cartoons simultaneously for the singular fiber in this degeneration. So my first cartoon is, it's the two cartoons I drew. So it's three varieties meeting transversely, or n varieties meeting transversely. So this is my first cartoon, but I'll also often draw this picture. Okay, I want to be able to flip between the two without apologizing. So certain parts of it are just easier to explain here, but the theorems they hold in general. Okay, so these are my pictures of x naught. Okay. So there are several steps. And the first step is how do you define Gromov-Witten cycles for a singular space like x naught, right? So this is a singular variety, still projective. So mgn bar x naught beta. So this is still a proper DM stack, proper DM, but it has no virtual class. Okay. Basically because the target is not smooth, and so that that has some knock-on effect for what the moduli space looks like, and so the obstruction theory is not two-term. Or in the language I was saying, it's no longer true that the variety sort of has a preferred expression locally as an intersection of two smooth things inside of a third thing. That word preferred is doing a lot of the heavy lifting. Okay. And so instead of the whole space, we should rather work with what's called the moduli space of logarithmic stable maps to the special fiber. So I want to explain a little bit about what this is without saying. So we heard something about log structures in Francesca's talk, but maybe I'll say something a little complementary. So I have this moduli space, mgn bar x beta, x naught beta. This is not such a well-behaved space, and the reason it's not well-behaved is because there's too many maps. The lesson to remember is there's too many maps to x naught that have nothing to do with the general fiber of the family. Okay, there's some irrelevance there. And there is a class of maps. So there's a class of smoothable maps from curves to x naught. So smoothable maps from curves to x naught, they're good for us. So what do I mean by smoothable? I mean you can smooth it to it arises as a limit of a smooth curve mapping to the general fiber. Okay? So it arises as the stable limit of such a family. So we like these people. Okay? But this is also not a good answer because it relies too much on the global geometry of what your particular x naught might be, and so you want to come up with some kind of compromise. And the compromise is log geometry. Okay? So the log stable maps, they sit in the middle. I'll give you some examples as well. So they sit in the middle. So the first thing you should know about log stable maps is that in this situation, in a degeneration, if the map smooths, then it's log. All right? Okay, so let me make that just a tiny bit more precise. This will have the advantage of actually being correct. Okay, so what we should pay attention to in this picture is that on X, which is our smooth, the smooth space, the total space of our degeneration, we have certain line bundles. We have, let's say, generalized, okay, so we have, let me just call it what it is. So it's O x naught I, so the irreducible components, all right, that's not how you say it, right, that, O x, let me just call it yi, all right, so the components of the special fiber, they're line bundles on the total space, right? It's a natural line bundle that you should be thinking about, and they each come with a distinguished section. And so we have these essentially Cartier divisors on the total space. Okay? And there's various relations between them. For example, the sum of all of these divisors should be principal, and various things. So, okay, so that's good. And so given C naught to X naught, we can restrict, maybe I'll call this map F naught. So this is given some stable map to the special fiber, we can restrict O x yi syi to C naught. And now we get a line bundle and a section on a curve. The section might be 0, but don't worry about that. It's just a line bundle and a section. It makes sense. So this is okay. Why do I need the F? Okay, F upper star, F naught upper star. Okay. So we have this. And this cares much less about, this is on the curve now, it cares much less about the global geometry of your fancy X, okay? And so what you can ask, ask for those maps, those C naught to X naught, such that these data, for all these things with these data smooth, rather than the whole map, okay? So I told you that the smoothable maps are good, and so that should make sense if I can, so that's compatible with what I'm saying. If I can smooth the curve with its map to x naught, then of course I get a smoothing of the line bundle section pair as well. But I can ask for the line bundle section pair on its own to smooth without the global map smoothing. Okay? When I say smooth, I mean, again, it's a limit. There's a family of curves with a trivial line bundle and the unit section that degenerates to this. Okay, so that's what we're saying. And so this is exactly m log gn x naught beta. Okay, that's what it is. Phrased in this way, so this is an accurate definition of the space, but phrased in this way, you're never going to be able to work with it. So the game in log geometry is to find some kind of formalism where this is not sort of a tautological, tautological. Shouldn't use that word. Where this is not sort of unworkable. Right? So you want some non-trivial characterization of this, and it turns out that log structures are one characterization, but the space of maps to expansions is another characterization, and there are a few others. Okay? So it's all about that. Fine. So the theorem here, this is due to Abramovich, Chen, and independently Gross, Siebert. I think Mark is here. This is around 2010, 15 years ago almost. What they prove is that MGN bar log x naught beta is, okay, so it has a virtual fundamental class. So there is actually a distinguished way to present this as an intersection of two smooth things inside of a third smooth thing, and therefore give it a class. So it has a virtual fundamental class, and this class is the specialization in the family of the one we're interested in. Okay. So the net of all of that technology, which, okay, it's sort of intimidating, but it's really, it is understandable in purely geometric terms. The output of all of that technology is that you get to move your problem from the general fiber onto X0. Okay, modulo insertions. Okay, so modulo the gammas that I mentioned, but okay, I'll say something later about that as well. Okay, at least as far as the virtual class is concerned, you can move the question from this general fiber which has no properties onto X0, which is likely to have more properties. Any questions about that?
Specialization is a virtual class, isn't it?
Yes, specialization of. Thank you. Absolutely. Yeah, so the moduli spaces themselves will not form a flat family. Yes, sorry.
Sorry, I didn't fully understand your sentence. So you asked that these data smooth.
Yeah.
These data being the pullback of the line bundle and the section.
Yeah, that's all. The pullback of the line bundle and section has to smooth. It has to be the degeneration.
Smooth mean?
So that there's a family of smooth curves degenerating to your curve. The trivial line bundle in the unit section degenerates to this one. So it's an art and stack. So there can be lots of limits.
I see. So smooth means that the section becomes what?
Yeah.
I see.
Trivial line bundle and trivializing section. Yeah. Which is what would happen. I mean, you just imagine what would happen for the smoothing family for the whole. Yeah. So if that happens, then it's log. If that doesn't happen, then it's not log. Any other questions? Okay. So the second bit, which takes us forward in time about 5 years, is the sort of first place where tropical geometry enters the story. So you'll have noticed that people who like to say words like these also tend to say tropical a lot. And this is sort of one of the reasons. Maybe this was step one, maybe. And step two is decomposition. Okay? This is also due to Abramovich, Chen, Gross, and Siebert, although this time there's a dash in the middle because they joined forces. This time, they did not join forces. So it's a story of march towards peace and unity in our domains. Okay. This is recorded, isn't it? I should shut up. All right. So what does the decomposition formula say? Well, this the special fiber. Sorry. I wanted to say one more thing. Okay. I'll come back. So the decomposition formula is a sort of downstream consequence of the fact that you can take x0 and normalize it. Right? So x0 splits into a bunch of pieces, and so you should believe that there's some consequence of that for the moduli space. For example, because I had a reasonable curve inside x0 and I normalize it, I get a bunch of curves in a bunch of places. What?
Obert, no sé si val la pena o no.
Oh, yeah.
Hi ha molta humitat, la temperatura és més baixa, però hi ha molta humitat.
Sorry? Okay, I have, yeah. Okay. Is everything wrong? Is that what that said?
Somebody said some other language.
Oh, okay, yeah. So it's right in English. That's good. Okay. All right. So let me say something about decomposition. In order to say something about decomposition, I have to give you a slightly more workable statement of how how log maps actually look. So a typical picture of a log map is the following. Typical log map. So now I'm going to switch to this simpler cartoon, okay, where I have these two components meeting transversely, just two components meeting transversely in the total space. And how you should, here's a typical image of a log map, is you imagine a curve that lives exactly in one of the two components, and then another curve living in the other component. There's nothing that maps to the double intersection. They match, so every time I have an intersection point of one component with this singular locus, I should have an intersection point of the other component also with the singular locus, so there can't be any unmatched people here. And also, Okay, so matching two curves, matching, but also with matching tangency order. Okay, so this tangency order matching is a sort of very important part of the story. So the story of, I mean, this is, I think, a sort of well-known principle. Trying to understand degenerations always lands you in the situation of trying to understand pairs. Okay? Because somehow you think of a degeneration as some kind of open set with a closed, a union of a bunch of open sets with some closed boundary, and so you need to impose some boundary condition. Okay? But a typical log map is a curve in one component, a curve in the other component, and then a boundary condition on each one that matches. Okay? And where boundary condition means scheme theoretically they glue, so it matches in the sense of the picture drawn, but also the tangency order, hopefully also in the sense of the picture drawn, they match. Okay? So, if you believed, this is a totally false statement, but if you believed that all curves look like this, then here's a guess for what happens to the virtual class. So you would guess that the virtual class, I'll just write, okay, let's write the whole thing, x naught beta. You would believe that the virtual class of the space of maps to the singular fiber should decompose as a sum over some indexing set, which I'll call little gamma and explain, of some little pieces, of some simpler pieces, where each gamma tracks a bunch of discrete information. Okay, so the discrete information is the dual graph of the curve up to some natural equivalence relation, the splitting of beta, the splitting of G, and the tangency orders. Okay. So you imagine your curve, you just take that picture that I've drawn here, right? So we're thinking about this as being a specialization, so it has to have the same numerical data, right? And so off the genus, kind of G1 is going to go on one side and G2 is going to go on the other side. Off the curve class, beta 1 is going to go on one side and beta 2 is going to go on the other side, some kind of effective sum. And then there are these, what else was there? Splitting of G, splitting of curve class. The curve itself then probably has to split into at least two components, so you can remember the sort of topological type of how the curve split. And finally, you remember the tangency orders. Okay, this tangency order is going to keep coming back. Okay, and so this is not true. The moduli space does not consist of a bunch of curves that look like this only. These are all in there, but there are more. But nevertheless, the theorem of Abramovich, Chen, Gross, and Siebert is that this formula nevertheless holds. Okay, the formula that, yeah, please.
What is the tangency condition for three components?
Yeah, so this gets more complicated, but okay. You can still measure it, right? So if you have a curve with a distinguished mark point mapping to something with two divisors on it, you can still pull back the function cutting out one, pull back the function cutting out the other. You just independently measure the tangency orders, right? But what a typical map looks like is more complicated. That's what happens. All right. So defining the tangency orders is not the hard part. Other questions? Okay, so where are we? We've moved the question. This is called decomposition. We've moved the question to a question about reducible curves of a fixed topological type on this reducible thing. And again, if you believed, the next part should also be believable. If you believe that this is what the curves looked like, well, normalize the x naught, split it into two pieces. Now you have a curve in one with some tangency order, and a curve in another with some tangency order. So that's all we're really doing. Okay, so this brings us forward 5 more years, and well, 5 and 10 maybe. So this is the degeneration formula. So this is going to take a while. Let's see how far I got. So, okay, so I guess the version I'm stating is partially in an old paper of mine, and then sort of refined so it's more useful in this present setting in this paper from last year with Davesh. And what it states, okay, so let me just explain what it's trying to do. So you fixed your, so at the output of this decomposition step, we're thinking about curves in a broken variety of a fixed topological type. So we know the genus that's going into every vertex, the curve component, sorry, that's going into every component, the curve degree that's going into every component, the tangency order that's where different components meet. We have all of that data. So we fix this little gamma. And this normalization map, so by normalizing x naught to these yi's, you can imagine that there should be something like a map, I'll call it split, so we remember that it's just splitting the curve. It goes from the moduli space of log maps with this fixed topological type to curves in every component, which is a product over vertices in gamma. Okay, so remember gamma is a graph, and its irreducible components, gamma gives you a dual graph rather, its irreducible components, so this is just like an MGN bar, its irreducible components correspond to the vertices. And now you want to study stable maps to y vi with respect to the natural boundary. So every component in your special fiber, the way I've drawn it, again, the silly picture, it's easy, each of your two irreducible components comes with a distinguished divisor on it. Okay? So this here really means maps with fixed tangency. Okay, so sorry, I said this thing about tropical, so what is the tropical thing? Gamma is a tropical curve, for those of you who like that kind of language. Okay, so gamma is what's called a rigid tropical curve, and that's often in these kinds of problems, if you degenerate enough, in fact, all of this data sort of collapses. There's nothing more than the rigid tropical curves, and these lead to these famous correspondence theorems in tropical geometry. Okay, but this is somehow slightly more general. Okay, okay, so the goal of the degeneration formula, okay, so what does the degeneration formula do? What does the degeneration formula, sorry, I should say all of this stuff, I should have said Junli in the case of two components. Like when I was, when I was still learning to spell. Okay. So what does the degeneration formula do? It expresses the push forward split lower star of this virtual class m log gamma in terms of natural cycles, Gromov-Witten cycles on the codomain. Okay, that's the goal of the degeneration. Okay, so 7 minutes. Okay, I think I probably have to make a choice. I think I'll say two things. So where are we now in the game? We've moved from this general fiber to the special fiber. The special fiber breaks. So the special fiber, because it's naturally a stratified space, right, into these irreducible components, you can refine the moduli space into a bunch of sort of roughly irreducible components as well. And gamma indexes these irreducible components, and they keep track of this data. And then you can split each of these by normalizing the special fiber, and you can go from the moduli space of log maps to some kind of moduli space of maps to a variety, one of the irreducible components, roughly, but with a tangency order fixed along the boundary. Okay, so that's what you have to do. Okay, so that's where we are. We're still quite far away from, so let's just consolidate. Where are we in the question of, these classes lie in the tautological ring, or these classes lie in the span of some classes that I already know? Well, I've sort of made the problem better because this is now on one of the irreducible components, but I've made the problem worse because I have to track what's happening to this tangency order. So in general, this is some kind of quite complicated condition. Okay. So let me say something about that. Okay, so okay, so there's maybe a okay, like this. So the degeneration formula. So involve some new ingredients. Let's say weird or exotic ingredients. Okay, and let me just explain briefly what they are. So here's your y. That's one of your components you're mapping to, and it comes with a divisor. And this time I'll actually draw it in an SNC case because that's important. And then you imagine a curve mapping into this with some fixed tangency order. Something like this. I'll even have a curve in the corner there. Yeah, why not? Let me move this. Okay. So I have this. This is my typical curve, this yellow curve here. And my moduli space is maps. So curves mapping to y, but with this tangency condition. And okay, so how can I evaluate such maps, right? So how can I impose conditions on such maps? Well, there's still marked points, so that's okay. But now there's some special points where the curve interacts with the boundary. And so you can evaluate to, for example, this point here should evaluate into this boundary divisor here. So there's an evaluation space, I'll call it EV, which is, this is a product of strata of the boundary of y partial y. Okay. So what you would if you got used to working with this problem, or if you've worked with this kind of technology before, what you would now want to say is that okay, for each yi, there's another in the degeneration. There's another component that meets this one along this divisor, and what you want to say is, well, I'll just ask for them to match. I'll impose a diagonal condition so that the curves match. And the weird thing about this feature, and one of the reasons why Junli was able to do this 20 years ago, and we're still sort of, working hard 20 years later, is that these classes, where you impose diagonal conditions on this space EV, are not sufficient to conclude a reasonable formula for this push forward. Okay? But one of the observations, sort of the key observation in this paper with Davesh from last year, is that you have to go a little further and allow something slightly more exotic. And the slightly more exotic thing is that you blow up the product along strata. Okay? So what you have to do is take this product of spaces. It's also naturally a simple normal crossings space. And you have to blow up the product in a way that may not be a product of blowups. Okay, let's just think through that again, right? Like a product of a blowup is very rare. A blowup of a product is very rarely a product of blowups. And so you need to allow exotic, what we like to call exotic insertions, which are classes from the blowup. Okay, and how you do that is a bit complicated, but it's very closely related to what Johannes Schmidt will talk about later on the logarithmic double ramification cycle. So it's the same. It's sort of born out of the same collection of ideas. So you need to allow, as it turns out, classes that come from blowups of this evaluation space. Okay, but your moduli space doesn't map to the evaluation space, so how do you get it up there? And the way you get it up there is by using some kind of virtual strict transform technology. Okay, so that's what makes these exotic, is they're sort of strict transforms under blowups of classes that we understand. Okay, and
that was a very specific blowup that you have in mind.
So it turns out any sufficiently refined blowup will do. And basically what's going on is there's a naive answer to this question. And that naive answer is wrong, because that naive answer involves some non-transversality of intersections, and so you have to remove that non-transversality, and then we've known since the dawn of time that you do that by blowup, but we sort of tell you what that condition is. Okay, so that's what it is. Okay, so now I'll state two final theorems, and then that will. Okay, so two statements, and then I will end. So we're still in this world where I'm working with log Gromov-Witten theory. So spaces of maps with tangency conditions. And although I've hidden the pain, it's really there's a lot of pain. Okay, so it's not such an easy thing to work with. So the following two theorems, let me state. So first, so both are in some sense invertibility statements. Okay, so for a fixed y partial y, the Gromov-Witten cycles determined by all exotic insertions exotic classes coming from these blowups, so this is the new ingredient, it turns out that they are equivalent in some monstrously complicated way. There's some way to go between the two sets of data. So they're equivalent to the set of ordinary classes. Okay. So what does that mean? So you pick some particular cohomology class on this EV plus, this blow up, and you compute some Gromov-Witten invariant. And what I'm saying is, well, that's well approximated by something non-exotic, which is actually just going to be the push forward of that class to EV. All right? So it's well approximated by that, but there are error terms, and we can control the error terms inductively. And so you should imagine that the set of all these numbers and the set of all these numbers is related by some kind of invertible matrix. There's some sort of large matrix that takes you from one set to the other set that we can't compute explicitly, but is good enough for these purposes.
Sorry, like a universal matrix or a matrix that depends on the target?
Universal matrix that depends on the combinatorics of the target. Only the combinatorics, like just how many divisors there are, basically. Nothing more than that. Okay? And for all smaller data. So if you start off with curve class beta, then you'll need smaller betas in order to find the coefficients in that matrix. And the second theorem is also sort of a similar flavor. And this is a good one to end with. So the logarithmic Gromov-Witten cycles of a pair y partial y, so y with a boundary, are determined again universally by some universal formula by the descendant ordinary theory. So back in the world we like, ordinary Gromov-Witten cycles of y and all of its strata. Okay, so in the case where the boundary of y is smooth, this is the kind of statement that is it has a long history. So I think the first instance of it is in some sense in Ravi Vakil's thesis, or maybe the Kapparaso-Harris recursion. But Maulik and Pandharipande, a sort of very influential paper about 20 years ago, proved this quite generally. And so the main new input is that in the SNC situation. Okay, so that in some sense goes for everything that I'm saying. So maybe I'll say just one word about what this descendant means. So what you should think, it's again one of these invertibility statements. So if you have a curve in a target, some divisor d, then tangency order is modeled by logarithmic Gromov-Witten theory, but it's also modeled by some kind of classical geometry, right? So you can imagine if I want some tangency order, order 2, for instance, what's that going to say? Well, you go up to the universal curve and you differentiate the map and you look for some kind of jet bundle condition or tangent bundle condition that says that that class should be tangent. Okay? So that leads you to inserting psi classes into your problem. Okay? So the class, to say properly, EV, so the evaluation class of D with insertion psi at that point, it roughly models tangency order 2. Now I say roughly in the same sense of that previous statement. It's only roughly tangency order 2, and they're correction terms. But the correction terms are sort of inductive, and so you can write down some absurd, uncomputable invertible matrix. Okay, invertible because it's upper triangular and has non-zero diagonal entries, as it turns out. And so all of these data and all of the log data turn out to be equivalent. Okay, so that takes us from smooth general fiber to this reducible special fiber. I sort of fix the topological type, I normalize, and then I get rid of the log structure by using these descendants. And then, okay, there's something I'm not saying about primitive cohomology, but it's all handled. And that, okay, so that gives you the theorem. All right, so I'm over time, so I'll stop there.
So, other questions?
So, in the theorem, goes back. So, when you break x into x naught, okay. So, how do you control all the classes on x? Like so, the theorem will say the Gromov-Witten cycle. I mean, if you can prove the theorem for x naught, then you prove it for x.
Well,
a lot of classes on x.
They don't come as restriction from the total space. Yeah, so that's a great point. So this is this statement about vanishing cohomology, Right. So it turns out the answer to that is also in this exotic insertions business. So what is the constraint? Okay, so the statement is, I'm interested in Gromov-Witten classes where the insertions don't come from the total space of the degeneration because a class has to be monodromy invariant in order for it to come from the total space. But let's remember that the Gromov-Witten the virtual class itself is also monodromy invariant. Right? And so that gives you a constraint. You don't need to study arbitrary Gromov-Witten classes, but some classes. Right? So it turns out that you do need to sort of enlarge your theory in order to accommodate the primitive cohomology. But the way you need to enlarge your theory is actually the same as this. So again, it's some blow-ups along strata, and this has to do with Deline's invariant cycle theorem. So Deline's theorem tells you that the cohomology of, if you had a smooth total space, right, which is this is some kind of moduli space setup, but if you had a smooth total space, then you can understand the cohomology of a general fiber the monodromy invariant cohomology of a general fiber by the classes that extend. And so you can extend classes, but on a blow-up, and so on that blow-up, you allow some new classes, and so those new classes turn out to be, they're taken care of by this part of the induction. So in the earlier work of Pierrick and Julia and Rahul Pandharipande and Dimitri Zvonkin, so their theorem is much more constructive. So this is some huge invertibility statement that you couldn't actually compute the invariance. In that case, they reduce the computation to some certain diagonal classes that are easy to compute. Okay, so that's something you can't hope for in general, but that's how you do it.
I did not understand the answer. What do you plot? Because you cannot change the monodromy.
No, you cannot change the monodromy. But so you think of the evaluation space, right? So the evaluation space is like the fibered product of your degeneration many times, and that's singular. But if you blow up that to make it smooth, that gives you some new classes. You're forced to study some new classes in the special fiber of the degeneration. And those classes are enough because your cycle is, what am I trying to say here? The cohomology of the monodromy invariant cohomology splits off as a direct summand. And that's compatible with like Poincare pairing and cup product and fundamental class and all of that. And so because of that, it's enough to just understand insertions that happen to extend to some smooth model. And so in order to get the smooth model, you have to blow up.
Any further questions?
So if you have a K3 surface which degenerates into some rational guys,
yeah.
Then for the reduced virtual class, what
do you say
using this method?
Right. So a student of mine, Ajit Kumaran, who's here, is thinking about this question. So so I think the theorem that you would want to prove is that the reduced Gromov-Witten cycles are all tautological. That seems gettable, but there's some things to do there. So there's some atomic input there, which is it's analogous to the following. So when you do Gromov-Witten theory of P2 relative to an elliptic curve, you have some more information. So you can refine the problem by like the torsion order of the intersection with the elliptic curve, and that's what you need to study the reduced class. And so how to incorporate that into the degeneration formula, he's still working on, but that seems like it'll be a solvable problem. Yeah.
Okay. Other questions? Okay. If not, we thank the speaker again.